So welcome back. We have started with the third module already, and that is what microwave tubes. So let's proceed further. In fact, we'll first revise what we have done and then we'll proceed further, because with the topic which we are going to discuss requires the previous working of devices. Okay, so as we said, the conventional microwave tubes like triodes and tetrodes fail above 300 megahertz due to these effects. So that's why we go to microwave tubes, and the transit time effect, which is a problem below 300 megahertz in fact, is used as a friend in microwave tubes, right? So that is the irony which is written here. So the tubes are klystron, TWTs and magnetrons mainly. So then we discuss, they basically work on the principle of velocity modulation, where the kinetic energy is transferred from the electrons to the RF wave for amplification or oscillation. So they are classified as O type and M type tubes, right? Next, so we studied this in detail. So O type tubes, what is the thing? That the electron beam direction and the electric and magnetic fields are aligned, right? So that's why they are called as O type tubes. So these are the classifications for O type tubes, which are also called as what? Linear beam tubes, right? So we have mainly klystrons in the syllabus, then TWTs, right? So twistrons etc. are not there, right? So we will not see them. So then if the electron beam is perpendicular to the electric and magnetic field, then it is called as M type tube. Okay, so they are also called as cross beam tubes, right? So we saw this. So in this we study BWO mainly and magnetron. So magnetron and BWO, today we are going to discuss these two, which are the M type tubes. So then this was the classification. So we studied also about octave bandwidth, where the right hand side frequency or the upper cutoff frequency is twice the lower cutoff frequency, right? And what is the main difference here? Kinetic energy is converted to RF energy, and in M type potential energy is getting converted to RF energy, right? And here, as we saw, the electric and magnetic fields are aligned. Here the electric and magnetic fields are perpendicular. So then we saw the acceleration of deceleration of electrons. I made a big mistake here in fact. So this I said is deceleration of electrons. This is actually acceleration of electrons. Actually it is a very simple reason why it is acceleration, because electric field gives which direction? It gives direction of a positive charge, right? So electric field arrow always gives a direction of positive charge. So that's why this electron will obviously get attracted here, okay, and here it will get decelerated, okay, and this is called as what? Velocity modulation. So it will not have effect in whatever I have explained, because anyways both things were anyways happening, right? But it will make a difference in magnetron, which we are going to study today, okay. So then we studied two cavity klystron. So what is it? It uses cavities. So cavities are what? Resonant structures. So again, if I take the example of 2 gigahertz, so if this cavity is resonating at 2 gigahertz, I can give input corresponding to 2 gigahertz only. So if I give an input corresponding to 2 gigahertz and I give the electron beam from here, from the cathode, it will get attracted towards the positively charged collector, and it will be focused with the help of these focusing electrodes. So since once they are traveling here, when they approach here at this point, what is happening? A input RF signal is given. So it is a AC signal. So it will generate an electric field here. So that electric field will oscillate in these two directions as shown here. So it will oscillate between this. So there will be continuous acceleration and deceleration of electrons, which is called as velocity modulation. So because of this, a point will come where the bunches will be formed. So once this bunch reaches here at this cavity, so these bunches are corresponding to which resonant frequency? 2 gigahertz. So since these bunches are corresponding to a resonating frequency of 2 gigahertz, they will induce a field here and transfer their energy here, because this can also resonate only at 2 gigahertz. So once it sees 2 gigahertz here, it will induce an electric field here because of the changing velocity, and that electric field will be taken out in an amplified format, right? So then we had said this important point, I have already mentioned that. So this is called as what? Again, apple gate diagram. So you have to draw this in working of klystron, as well as if velocity modulation is asked. So if the electron is corresponding to 0 potential of the electric field, what will happen? It will have no change in velocity. But if it is at coming with positive, what will happen? It will be accelerated, right? And if it is negative, it will be decelerated, right? So at a point a bunch will be formed. So this is the process of velocity modulation. So yeah, so then what was the problem with two cavity klystron? Its gain is relatively low. So what we do, we introduce multiple cavity klystrons. So between those two cavities we can insert 1, 2, 3 or 4 more cavities. So the bunch which is formed here comes here, it induces, here output is not taken, remember, the output is taken here. So this bunch induces electric fields here which further enhance the bunching. So here more stronger bunches are formed. So this stronger bunch again comes here and we get an amplified output as compared to the two cavity klystron. So that is the working of klystron. Then we studied what is staggered tuning. What is staggered tuning? The cavity is corresponding to one resonant frequency only. So if you have a multi-cavity klystron, all are tuned to different frequencies. What will be the advantage? The bandwidth will increase. Okay. So that is what we studied in staggered tuning. So then reflex klystron, how it works? We have a main part as repeller here. It is biased to negative voltage. And here we have the electron gun. So how does it? So it will emit electrons, right? So what will happen? Am I recording? Just let me check. Yes. So this electron gun, what it is doing, it is continuously bombarding electrons, and obviously it should be negative potential, and the positive and the connection is such that the cavity is made at positive potential, so they get attracted here, right? And these are accelerating gates which also act as focusing electrodes. So they are it is called as a collimated beam. So what happens, they try to go in the upward direction, but after some space they experience this repeller space. In the repeller space they get repelled. Why? Because this is again negative voltage and electrons are negatively charged, right? So because of this repel they get back and strike here in the cavity part. So how the oscillations are sustained, that we'll see from this diagram. So since this is a cavity, it resonates at a particular frequency. So remember, this is an oscillator, so you don't see anything as input here, right? Because it is oscillator. Oscillator doesn't have any input. So you might have a question, sir, there is no input, so from where we get the RF signal? So when this DC source is switched on, it is not a ideal source, it is a practical source, right? So there will be some fluctuations at the start. So because of this fluctuations, or which we call as noise in the circuit, the frequency, so all the frequencies are generated in this noise. So corresponding to the resonant frequency of the cavity, that the frequency can be sustained. So how we achieve that sustaination is using this repeller space. So when the electron beam is bombarded in this way, if the electron is corresponding to point B, what will happen? Since it is corresponding to zero potential, it will neither be accelerated nor decelerated. But electron corresponding to point A, since it is at positive potential, will be accelerated. So it goes farther than electron B, but eventually it gets repelled, right? So what happens to electron C? It travels with less velocity, reduced velocity or deceleration, because it is at negative potential. So it travels less and gets decelerated. So this is having less velocity, normal velocity, and more velocity. So a point will come where they will bunch. So this distance T0 is set such that all the electrons form a bunch corresponding to positive potential of the RF wave. Okay. So what will happen? So this bunch, once they come here, they will give their energy to the RF signal. So in this way, sustained oscillations will be produced. Okay. So now remember, the oscillations will not be sustained directly. First the losses will be incorporated, and corresponding to that the oscillations will be sustained. So when the losses are incorporated, then the oscillations are sustained. Okay. So then we saw the modes of oscillation. So as I said, corresponding to this distance we get the sustained oscillations, right? So depending on this distance we have various modes. So if you see this T0, this is 3 quarter cycles, and the capital T is what? The time period of the signal, right? So this is corresponding to 3/4 mode, and this is corresponding to 1/3/4 mode. So this is T0 equal to n plus 3/4 times T, which is nt, where n is n plus 3/4. So then we studied slow wave structures, which are mainly used in M-type devices. So these are the various forms of slow wave structures. What do slow wave structures do? So if you see if the RF wave signal is passing through this, it has to travel a large distance as compared to a straight line. So since it is traveling a large distance, its axial component of the electric field will experience. So you'll have a axial component of electric field here, right, which is used in helix TWT. So since it has to travel a larger distance, its axial velocity will be less than the speed of light. So this is how the slow wave structures are used. So simple explanation is what RF travels at speed of light and electrons travels at a speed less than that of light. But if you want them to interact, so their velocity should be approximately equal, right? So hence we use slow wave structures. So how we achieve? By artificially increasing the distance that the RF wave travels. So these are the various forms of slow wave structures. So this is asked for 5 marks. So we studied a very important microwave tube, which is helix traveling wave tube. So where is the slow wave structure? It is this in helicon form. That's why it is called as helix slow wave structure, right? So we take the input from here and output is given here. So if you see, the wave is traveling like this. So the axial component of electric field will be towards right, and since it is oscillating, at one point it will be towards right, at another instant it will be towards left, right? And electrons are continuously coming from here. So again we'll have acceleration and deceleration of electrons. So they will form bunches, right? So these bunches will again deliver power to the RF wave. How they will deliver? Again it is mentioned here. So what is the important thing which you saw last time? The DC velocity of the beam is maintained slightly greater than the phase velocity of the RF wave. So what will happen because of this? More electrons face the retarding field. So if more electrons are facing the retarding field, means what? More amount of energy is transferred to the RF wave. So I had given a simple example. If you are running very fast, right, and if you try to stop immediately, you are not able to stop, right? So when you apply retardation in one sense, so you are going a big farther, right? So that is what is happening here. So when they experience a retarding field, they have to going a bit farther is translated to what here, that the energy is transferred, okay, because your energy is also transferred somewhere when you are trying to stop immediately. You are not able to stop immediately, right? So that is the same thing ever happening over here. So this is how oscillations are achieved, okay. So then this is the thing how the oscillations are achieved. Remember, if you have a doubt that this is an unstable thing, they are not getting amplified continuously. It is shown that in the circuit they are getting amplified continuously, but once the losses are incorporated, we will get a continuous wave output. So along the length it is getting amplified, but once the losses are incorporated, it will be a stable output. So then this was the difference and advantages, applications. So next device is a M-type device, which is a backward wave oscillator. So what are they? They are very high power microwave devices, and they are capable of giving powers in the multi-gigawatt range. That was not the case with klystron, okay. So we saw it is a low power device, right? So this is a high power microwave device. So that is why we studied this also. So it is also called as carcinotron, okay. So this you can study. So and it is a frequency tunable device, means you can operate it for various frequency ranges just by changing the electron beam voltage. So this is the simple structure of the backward wave oscillator. So what was used in helix traveling wave tube? A helical structure was used, slow wave structure, right? So this was a helical slow wave structure. So here what we are using, a rectangular slow wave structure. So again, if the RF signal is directly going like this, what will happen? It is traveling like this only. But if I make it to travel in this way, it is traveling a larger distance, right? So somehow we are trying to reduce the axial velocity of the RF wave. So that is why this is also a slow wave structure. So what is happening? The electron beam is going from this path. The holes are cut through this structure here. So corresponding to this, in this the RF signal will be generated due to noise, again due to this DC noise, right? Again there is no input here. So that RF signal will induce electric fields here. So they will again oscillate from left to right and right to left. So again there will be velocity modulation, right? And we have seen in all these devices that once we achieve velocity modulation, energy is transferred from the electron beam to what? To the RF signal, right? So once the power losses are incorporated, we will get sustained oscillations. Okay, so now one thing you should understand is what is the difference between this oscillator and the helix traveling wave tube. Okay, and why this is called as a backward wave oscillator, so that we need to understand. Okay, so for that we refer to this something called as dispersion diagram. Okay, so now we have studied Vp. What is Vp? It is omega by beta. So if you remember, in electromagnetics we said that the medium is dispersive, right? In microwave only, in waveguide chapter we said that the medium becomes dispersive, that waveguide is a dispersive medium. So this is also but nothing but a rectangular waveguide sort of, right? So this is a dispersive medium. So that is why what will happen, depending on the frequency, the phase velocity will change. So when we say that the phase velocity is dependent on frequency, we say it is a dispersive medium, right? So for different frequencies we'll have different velocities. So that is what this diagram is showing. So that's why it is called as dispersive diagram. So if you see, on y-axis we have omega, on x-axis we have beta L. So you can neglect this L and think that it is a beta only. So y by x is what? Vp, because it is omega by beta. So the slope of this line gives what? The phase velocity. So this is what the dispersion diagram plotted. So it is going upwards, attaining a maximum value, and going downwards, so sort of a bell curve, right? So if you take a line and from the origin and plot it on any point on this curve, what you will get? A positive slope, right? So this positive slope, if you extrapolate, this is y, this is x, right? So you are getting a y and a x, and the slope is positive. So this is what? A positive phase velocity. So this slope gives at this point the phase velocity value. So you will have a value of omega, you will have a value of beta. So you can calculate the value of Vp, right? So the slope is what? Positive. So the slope phase velocity is what? Positive. And what is Vg, group velocity? So what is group velocity? The velocity which actually carries the information is the group velocity. So it is given as what? Derivative of omega with respect to beta. So d omega by d beta, right? So this is the curve for dispersion diagram, right? So if you want the derivative of this, derivative is nothing but what? Again a slope. So that if you calculate, it is this slope. Okay, so what is this slope? Negative. Means what is happening? The phase velocity is positive, but what is happening to group velocity? Negative, right? So if I operate from pi to 2 pi, what will happen? You will always get a positive phase velocity and a negative group velocity. But let's say I operate the device from 0 to 2 pi, what will happen? Phase velocity will be positive. What about group velocity? So if you take the derivative at this point, now how will you take the derivative is, let's take this example. So this is going downwards, right? So you will take this y-axis and this x-axis. So if you have this y and this x, the slope is like this. That's why I am getting this slope. But if you take this phase velocity here, it will be here like this. Phase velocity is positive. But what will happen to y? Y will be here and x will be on the opposite side as compared to this. So y is here, x is here. So slope will be like this. So again slope is positive. So if you operate from 0 to pi, Vp is positive as well as Vg is positive, right? So the wave is traveling in the forward direction, we say. That is the concept here. So that was happening in a TWT. It was operated from the phase shift of 0 to pi only. So the wave was traveling forward only. So that is why it is a forward wave device. But what happens in a backward wave oscillator is, it cannot be, it is operated from pi to 2 pi. So phase velocity is positive but group velocity is negative. Means what happens? The wave actually travels backward, and that is the reason we take the RF output here, because the wave is traveling backward. Okay, and that's why it is called as backward wave oscillator. So that is the essential difference between TWT and BW. And TWT is amplifier, but this is a oscillator. Okay, so this is the working of BW. So let's go to the main device which is usually asked in the exam apart from klystron and TWT, which is magnetron. So as we studied, all the devices we studied apart from BW were O type or linear beam tubes. So the other types are M type. So basically it is a magnetron. It is again a oscillator, and it is again used for high power. So it is used in microwave oven. So if you cut open your microwave oven, you will see a circular structure. So that circular structure is nothing but magnetron. And why it is called as microwave oven, if you have thought about it, is because the magnetron which is stored inside the oven, it works at a frequency of 2.45 gigahertz. So we have studied in microwave that the frequencies above 1 gigahertz or in the gigahertz range are microwave frequencies. That's why it is called as microwave oven. So what happens in the oven is due to this magnetron only. Okay, so let's see how it works. So it is a circular structure. Okay, so we have a circular cathode in the center, okay, surrounded by a circular anode, and we have some slots made in the anode. So these slots are what? This is the slot and this is what? A cavity, right? Similar to klystron. Okay, and we give obviously a negative voltage to the cathode with respect to the anode, right? So this is the way, and we have an external magnetic field with the help of a permanent magnet given in the z direction. Okay, and we get the output from any one of the cavities. So if you want, you can show the output from here also. So this is a coaxial output, so that is why this output coupling loop is shown. Okay, so this is the simple construction of a what? A magnetron. So this slide is taken 2 times by mistake. So this is the anode. If I see from the top, I'll see this structure, right? So this is the cathode, this is the anode, right? So what is happening here is, what is the force? You know, force is QE, where Q is the electric charge, so that is written as E here, and it is minus, you know that. We have seen this in electromagnetics and your basic physics, not in electromagnetics to be precise. So F vector is what? Minus EE. So because of the cavities, so again what will happen? You don't have, since this is oscillator, you don't have an input. But again, when the source is switched on, due to fluctuations in the DC source, a noise corresponding to resonant frequency of these cavities will be generated. So from that you will get a RF signal. So what happens because of that RF signal? Electric field will be induced in the cavity, as we saw in klystron. So because of that electric field, we'll have F vector is minus EE. And since we are also giving a magnetic field, the expression, to that expression, this minus E times V cross B is added. So V is what? The velocity of the electron. So this from this expression, the whole understanding of magnetron is coming. Okay, so let's say the electric field is, the magnetic field is 0 initially, right? So if there is no magnetic field, means what happens when the source is switched on? We only have the electric field, right? So electric field will be here and the cathode is here, right? So what will happen? F is minus E, right? So only the electric force is acting. So this is a cathode, this is anode. So electron will obviously get attracted towards the anode, right? So that is what is shown here. Okay, so from the cathode, the electron A travels towards the anode, right? So this is the first case for B corresponding to 0. Now let's take the second case of electron B. Now let's say there is a magnetic field, but it is less than the critical magnetic field. Now what is critical magnetic field? We'll see in some time when we come here. So let's assume that the magnetic field is less than the critical magnetic field. So what will happen? Earlier the B was 0, so only electric field was acting, so it was getting attracted to the anode. But now, apart from E, a B force is also acting, a magnetic field B is also there. Where is the velocity vector? Velocity is towards the anode. And where is the magnetic field? As shown here, it is going into the cathode. So here in this case it will go inside the paper, right? So velocity is here toward downwards, I can say, and electric field is inside the slide or inside your smartphone, right? So what will happen? Or your laptop. So what will happen? We have seen X cross Y is Z cap, means the where will the electron trajectory go? Perpendicular to this V cross B, right? The cathode will attract it here, but V cross B, what it will do? The electron, it will try to take the electron to the perpendicular plane of V cross B. So V is going downwards, but B is going inside. So it will travel towards left, right? So that is why we get a curved trajectory for electron B when B is less than BC. Then there is a critical value of magnetic field where if you increase the magnetic field further, the electron just traces the anode part and returns back. Again, why does it return back? Because you are applying a magnetic field. Okay, so because of that, it follows a curved trajectory. To complete the curved trajectory, it has obviously again hit the cathode. Okay, so and obviously it damages the cathode. So if you might have a doubt that how can it hit the cathode, obviously it will damage the cathode, so we have to take care of it. So that is a different thing. So That is a design problem, so we will not discuss that. So when magnetic field is equal to the critical magnetic field, the electron just traces the anode part and returns back. Why does it return back? Because of the experience of the magnetic field, because it has to follow a curved trajectory because of this V cross B. Okay, so that is the reason it again returns back to the cathode. So at one point, if you are keeping the magnetic field greater than the critical magnetic field, what will happen? It will not trace the cathode, since it has a higher force now. So it will go earlier to the, it will take a lesser path and travel back to the cathode. Okay, so this is the main concept you should understand before understanding the working of magnetron. Okay, so then there are various modes of a magnetron. Why there are various modes? Because you have various cavities, right? So because of that you will have various resonating frequencies if all are not tuned to the same frequency, right? So that is why the concept of mode comes here. So the nature of field distribution in the magnetron cavities is such that the alternating RF magnetic flux lines pass through the cavities parallel to the cathode axis, right? So this is the cathode axis and the magnetic field is along the axis, so that is what is said there. Okay, and the alternating RF electric fields are concentrated across the slot. That is, you have this slot here, right? So the electric field will be between these two vertical lines, as we saw in klystron. So that is what is written here, right? And they fringe out to the interaction space, means they come out and fringing happens here, as we saw in microstrip antenna. So this fringing out means that fields will come out here. So that we'll see in the further slide again. So if you have n resonant coupled cavities, there will corresponding to n resonant frequencies or modes. Because they are different frequencies, we can call them as modes also. So for if you have 8 cavities, we'll have 8 different modes. Okay, so these are called as resonant modes. Okay, so corresponding to this magnetron, we have this equivalent circuit. So each cavity corresponds to this LC parallel circuit. Okay, and what is this diagram, we'll see in some time. Okay, so now from Barkhausen's criteria, we know that for sustained oscillations, phase shift would be 360 degrees or 2 pi, right? So corresponding to our number of cavities n, we'll have the phase shift between two adjacent cavities as phi n equal to 2 pi into n by n, where small n equal to 0, 1, 2 to n by 2. It indicates the nth mode of oscillation. Now we want, so obviously there will be one mode which is more suited for the oscillation, so that mode is the pi mode. So it is observed that if you have opposite phase in successive cavities, means if we have the electric field above, pointed above in this cavity, it should be pointing downwards in this cavity. So means there should be a phase shift between these two cavity, so of 180 degree. So if you have a phase shift of 180 degree between successive cavities, it is called as pi mode, and the excitation is maximum. So this is beneficial for us. That's why almost all the research is going on pi modes in magnetrons. Okay, so this is achieved when what, n equal to small n equal to n by 2, right? So n will get cancelled and 2 will get cancelled. Okay, and usually for that we use 8 cavities, so that is why you see 8 cavities here. So in your construction also, ideally you should show 8 cavities to indicate pi mode of operation. So then there is something called as mode separation and mode jumping. So what is this? Now each mode corresponds to a different frequency, as we saw here, right? So for n resonant coupled cavities, there are n resonant frequencies or modes. Means for n cavities we'll have n modes. So each mode corresponds to a different frequency. So what is the problem because of this? The various modes are detuned differently from fundamental resonant frequency, right? So as we saw, if you want a good sustained oscillations, we obviously require all the cavities to have the same frequency, right? But that is not the case usually. There is some changes in the dimensions. Because of that we'll have different resonant frequency for each cavities practically, right? So what happens this? Because of this makes it difficult to separate the pi mode from the next immediate mode for maximum excitation, right? For example, this might work at pi mode, but this might work at pi by 4, this might work at 3 pi by 4 because of the changing dimensions of the cavity. So this is called as mode separation. Okay, and because of this, what will happen, since this cavity is having a different mode, this is having a different mode. So from here it will jump to the other mode, from here it will jump to the other mode. So mode jumping and mode separation is occurring. Okay, so what is the difference between mode separation and mode jumping? So mode separation is the difference in frequency of the modes. Okay, so you can say owing to the changing dimensions of the cavities, so that may be due to a problem of fabrication. And what is mode jumping? That the device starts operating in different nearby modes than the intended one. For example, we might want to operate the device in pi mode. Okay, so but the successive the different cavities will have different resonating frequencies, so it will not operate exactly in pi mode. So that is called as mode jumping. So then we finally come to the working. So how does actually the mechanism of oscillations is sustained, or the oscillations are sustained in a magnetron? For that I have just made this punch points. So again, you don't have to by heart how it works, so just understand the concept and will be good enough. So the first thing is, we saw the 4 cases here, right? So we saw the 4 cases. The most suitable case is B should be greater than BC. So we keep the magnetic field such that it is greater or it is exceeds the cutoff value. Okay, so then we have take the example of 2 electrons, A corresponding to retarding field and B corresponding to accelerating field. So let's go to our acceleration and deceleration slide at the very start. So when does the electron accelerate? So when the electric field and when the electric field and the electron beam are in opposite direction, we get acceleration, and when they are in same direction we get deceleration, right? So this concept is used in magnetron again. So let me go to that slide. Yeah, so A is observing a retarding field here. How? So if you see here, the electron, once the source is switched on and the DC magnetic field is exceeding the cutoff value, so it will not trace, right, because it is greater than the cutoff or critical magnetic field value, so it will go till somewhat here. And what I meant by fringing is, the electric field will be generated in the cavity, right? So it will come out of the cavity also due to fringing. This happens, this is observed practically. So this is called as fringing fields. So this is called as fringing, which was discussed earlier. So, and since the DC magnetic field is exceeding the critical value, it will not hit the anode. So it will not hit the anode, so it will be somewhere here. So what is happening? The electron direction is towards up and left, and the electric field is also in the same direction. So since they are in the same direction, as we saw in the previous slide, there will be what? Deceleration of electrons, right? So again I will show you. So they are in the same direction, so there will be what? Deceleration of electrons, right? So that is what is done there. Deceleration in the sense there is a retarding force, we can say, right? So they are in the same direction again, so we will experience a retarding force. And if you take the example of electron B, this is the electron B, right? It is going like this towards left, but the electric field is coming towards right, so it experiences a accelerating force or a accelerating field, right? So what happens to A? Since it is experiencing a retarding electric field, so F is what? We saw the formula, minus EE. So E is reduced, right? So because of that it will experience what? A reduced force, right? What is that slide? Yeah. So A experiences a reduced velocity and therefore a reduced force. So since it experiences a reduced force, it will tend to go towards the anode, right? More towards the anode, right? So that is why you observe this is going further toward the anode because of the retarding field, right? So, and what happens because of this? It goes towards the anode, and what we do, we adjust the DC anode voltage and the magnetic field such that the velocity is changed. So how we want to change the velocity? We change the velocity such that it travels from this slot to exactly this slot, and it travels in this much path only, without going more to the anode and without going more towards the cathode. So we adjust the anode voltage and the magnetic field such that it travels in this direction and along this path. So what happens? It is experiencing a longer duration of experiences retardation for a longer duration of time from this slot to this slot. So almost for half of the oscillation of the RF signal, right? So this is at one peak, so this is at other peak. So it is experiencing for one half of the RF signal it is experiencing a retardation field, right? And we have seen right from klystrons that if the electron experiences a retarding field, it was traveling with some velocity here, it experienced a retarding field once it came in the purview of this electric field. So once it experiences a retarding field, what will happen? It will continuously give out energy to the RF field. So this RF field, so this electron will continuously give out the energy to the RF field till this point, right? So after it is going here, again it is experiencing same force. So what will happen? Finally it has to hit the anode, right? So finally it will hit the anode, right? So this is how energy is given to the RF field. So once again it incorporates all the losses, these oscillations, so the energy is continuously given to the RF signal and we'll get sustained oscillations in the circuit. So what will happen to the electron B? Since it is getting accelerated, so it will go faster to the cathode and hit it, right? So it is experiencing the field for a shorter duration of time. So energy is not lost here because of this, because it is experiencing acceleration only for shorter duration of time. So again the energy is transferred only when it is in retarding field. So from accelerating field we will never be able to extract energy. Okay, so that is the simple working of a magnetron. Okay, so again I have taken this magnetron working mainly from Annapurna Das book, and most of the other things are taken from Vinit Chauhan. And BWO, this dispersion diagram you will not find in books, that I have taken myself from other books which are not in the syllabus. Okay, so make sure you write this. Okay, so anyways you will get notes for this, so you don't have to worry about it. So we'll stop here.